Hi, we are the Cool team and we designed an air cooling system. I'm Shahana.
I'm Hector.
And I'm Max.
There you go.
My name is Max Roth.
I'm Hector.
I'm Shahana.
We're the Cool team. So this is actually a modification of our senior design project where we're building a cooling system for a electric vehicle conversion kit. This is a scaled down small version. So the way that it works is we have two different temperature probes here. And as you can see on this display, as they're above 26 degrees, that means that the motors are too hot and they need to be cooled. As soon as they drop below 26, they turn off. Notice how it's 25 degrees. As we heat them up again, the fans will turn back on. Okay, now notice we have a safety feature, so when the hood of the car opens, the fans automatically turn off. And they turn back on once the hood is closed.
There you go.
All right, so you just saw there a brief high-level video of our demo. Here's another one again without audio, so we can kind of talk over some of the high points of the module. So we designed a housing unit to house these made out of 1/4-inch polycarbonate with two isolated chambers, one for our fans and one for our circuitry. In the unit that has the fans, we have an ultrasonic sensor, which is our safety feature. So essentially, we have a hood indicator, so that way whenever this lid is opened, the fans automatically turn off, regardless of whatever the temperature reading is. And when it closes, they will turn back on only if the temperature is within the threshold. You can see on the left, we also have a power supply. We have our relays for our fans, our microcontroller, as well as some other additional small components that we learned about in 106, including a transistor. Here you can see on our digital display, it says closed, which means the hood's closed and the fans are on, which means that the temperature was high. You can see it just clicked there, fans are off, and that must be because the temperature dropped below the threshold, which for the purposes of this demo, we chose 26 degrees, but for our senior design project, as mentioned, is 115 degrees Celsius.
A flowchart of our subsystems. So as you can see, sensors and the ultrasonic distance sensor sends measured information to the Pico. The Pico is programmed to open or close the relays to control the fans. And then the display will show the temperature measurements and the status of the fans and whether the hood is closed or open. Here is the breadboard schematic for our system. To do this, I bought an IoT starter kit and we used the instructions given in that to connect all the sensors. And the components we used are the DS18B20 temperature probe sensors, one channel 12 volt relay module, two 12 volt fans, and the HC SRO for ultrasonic sensor, and finally the OLED display, which is a 128 times 64 pixel display screen. And finally, each of these sensors use a 5 volt input, including the 12 volt relay and display. The fans use a 12 volt input and we power it through the relay. For the software, we imported the time library, the UTime library, the one wire and the DS1820 library, and the SSD1306 library. The one wire and the DS18 library is for the temperature sensors, and SSD1306 is for the OLED display. So as you can see, we first set up each sensor, and then we created a while loop, and inside the while loop, we created condition statements that controls the system as we need.
Okay, just to talk a little bit about our box design and our construction. So this is the CAD for our box, dimensions 8 inches wide, 4 inches deep, and 14 inches long. As mentioned, we have the two different sections here and a hinge that we have attaching the lid to the box. So what we did is we actually worked with Tap Plastics in San Jose to get 1/4-inch polycarbonate, and we solvent bonded this box together ourselves. So we deburred the edges, cleaned everything, and we used gloves and masks and did it all properly and safe, but we solvent bonded this together. So it's a really strong, nice box. It showcases all the circuitry and the fans really well. Essentially, this is a scale model for our senior design project. So we wanted to make sure that it was something that we could make the argument that it could look nice within an engine bay. Obviously, the fans would be outside the box and they'd be directed directly towards the electric motor module. But we wanted something that looked professional and clean.
So some of the issues that we had with troubleshooting was actually troubleshooting. We thought we gave ourselves a large enough window to account for it, but we ended up falling behind anyways. So other issues was with our first choice for the motion sensor. Initially, we used a PIR sensor, but after doing research and some testing, we realized that the PIR sensor was too sensitive for the motion detection, because it uses infrared to sense motion. So instead, we decided to switch to an ultrasonic distance sensor. So we were able to set a condition statement to activate the system and deactivate it as well, depending on what the nearest object was and when it detected it. We also had issues with the relays. So initially, we wanted to use one relay for each fan, but at the last minute, of course, what happens is we damaged one while testing it. So we had to rewire our system so one relay could control both fans. This was only possible because we built a small scale system, but for an actual scale automotive cooling system, it would be safer to use one relay for each fan. Initially, we used two DHT11 temperature and humidity sensors. These sensor measures the ambient temperatures, but we decided that because we couldn't control the ambient temperatures, we decided to go against them. So we switched to the DH18B20 temperature probe sensors, because that allowed us to heat up the temperature probes easily without activate the cooling system at the temperatures that we chose. So overall, our model functioned as we intended. We used a Raspberry Pi Pico as our microcontroller, a temperature probe, and an ultrasonic distance sensor as both our sensors, and we used fans as our actuator, and a display as well. So if we were given more time to do this project, we would like to have cleaned up our wiring to make it look cleaner, and we would also like to have a better casing for our system, just to mimic the hood of a F-250 to give a better representation of how the system is supposed to look like. So my contribution was co-lead on the design to the house system. I also assisted in the troubleshooting system, report writing and presentation, and I tried to the performance evaluator for timely completion of tasks.
So my contribution is that I was the software and hardware lead. I researched on how to configure the circuit system, and I also assisted in troubleshooting the system, report writing, and the presentation.
And I was the design lead to the housing system and the box, the construction of the box. Also helped with some of the hardware, assisted in research of the electronic components, and also troubleshooted the systems. I also assisted in report writing and the production of this video. Thank you, everybody.
Thank you.